Hello everyone. Let's have a fifth method of numerical techniques for solving equations. Fixed point iteration method. Actually, in Newton-Raphson method, we have a hint for this prerequisite fixed point iteration method. So, in fixed point iteration, we have to consider the function in the form of x equal to phi x. So, in this case also, we have to consider the function as a sufficiently smooth functions. That is, the function is continuously differentiable sufficient number of times. And also the equation roots of the equation f x equal to 0 are simple, very simple. And the first of all, the first step, we have to first reset. This is very, very important. We have to first reset the equation in the form x equal to phi x. X equal to phi x. The equation f x equal to 0 is first reset in the form x equal to phi x. We find by the method of tabulation a sufficiently small interval a naught b naught containing the only root alpha of the equation f x equal to 0 such that f a naught f b naught less than 0. We assume that phi x is continuously differentiable in sufficient number of times. So ultimately this resetting is very, very important. That is, you have to reset the equation x equal to phi x. Suppose you have an equation 10 to the power x minus x plus 5 equal to 0. So you can reset the equation in the form x equal to 10 to the power x plus 5, or you can reset x equal to log 10 base, right? Log 10 base 5 minus x, right? In this way also you can reset the equation. So there are several things you can reset the given equation in many forms. So that is very, very important in fixed point iteration. You have to reset the equation in the form of x equal to phi x, and provided that phi x is a continuously differential sufficient number of times. So this is very important point. First of all, you have to do it like that. Next, this iteration is generated by the formula. This is an iteration process like bisection. The iteration formula is xn plus 1 equal to phi xn, starting with x naught equal to a naught or b naught. And the error epsilon n can be calculated by the equation epsilon n equal to alpha minus xn, where alpha is the exact root and xn is the nth approximation of the root. Now since alpha equal to phi alpha, because your x equal to phi x, you have reset the equation in this form. So alpha equal to phi alpha, so you can write alpha minus xn plus 1 equal to phi alpha minus xn plus 1, and that is equal to phi alpha minus phi xn, because xn plus n 1 is phi xn. And you can write, you can manipulate the equation like this, and by Lagrange's mean value theorem you can write phi dash xi n epsilon n plus 1 equal to alpha minus xn phi dash xi n, where xi n is the minimum of alpha xn and maximum lies between minimum and maximum values of alpha and xn. Okay, have you understood this step? Okay, so epsilon n plus 1 can be, error term can be calculated like this. This is a very important relation. So, and alpha minus xn is again epsilon n. So you have, this will be epsilon n plus 1. So this is the error equation. This is your error equation. Now let k denote the maximum value of phi dash x in a naught b naught. Then modulus of epsilon plus 1 equal to modulus of epsilon n modulus phi dash xi n. less than equal to k epsilon n mod epsilon n, because k is the maximum value of phi dash x in a naught b naught. Therefore, modulus of epsilon n plus 1 less than equal to k epsilon mod epsilon n, and epsilon mod epsilon 1 less than equal to k epsilon mod epsilon naught, mod epsilon 2 less than equal to k mod epsilon 1, etc. So you have a series of error equations. Successively you are substituting n equal to 0, 1, 2, etc. Finally, if you multiply the respective sides, it will cancel out. Some terms will be cancelled. If you multiply the respective sides, you will cancel epsilon n, you will cancel epsilon 1, epsilon 2, etc. So lastly, you have a mod epsilon n less than equal to k to the power n epsilon naught. Okay, and if k less than 1, this term will be 0. Limit n goes to infinity. This should be epsilon n plus 1. Sorry, yeah, this is epsilon n goes to 0, right? So this goes to 0. So limit n goes to infinity, alpha minus xn tends to 0 equal to 0. So limit n goes to infinity, xn equal to L alpha. Hence, the condition of convergence is k less than 1 or modulus of phi dash 6 less than equal to 1. So that proves that the condition of convergence of the fixed point iteration is k less than 1. So that is very, very important. And also you have seen that for Newton-Raphson method also, the condition of convergence is modulus of phi dash x is less than 1. Okay. So let's have a diagram. So in this case, you see this is your exact root alpha, and this is your approximate solution x naught, and this is the curve. And you see in this case you have mod this curve. Actually in this case you have mod phi dash x less than 1. That is the condition of convergence. So in this case you have staircase solution. This type of solutions are called staircase. It's like a stair. Okay, in this case you have a staircase solution, and that converges to the root alpha. If you this is also another approximation of the root. In this case also you have a staircase solution, and that also converges to alpha. So let's have a beautiful diagram. Look at that. In the first case, mod g dash x less than 1. So you have a spiral. This is called spiral solution. This is called spiral solution. You look at that. It's mod phi dash x less than mod g dash x. In this case, the function is g dash x less than 1. So your solution, actually spiral solution, gets decreased. So this is convergent. In this case also, the right hand side also, this is staircase solution. Look at that. You have a staircase solution. This is spiral solution. Okay, it's diminishing magnitude. Okay, and so in this case you have xn tends monotonically to the root alpha from with diminishing magnitude, oscillates. You see xn oscillates about alpha. In the first diagram, this is your diagram 1. So in the first diagram you see xn oscillates. This is possible if minus 1 less than g dash x less than 0. Okay, this is possible. In this case, your error equation will be epsilon n plus 1 epsilon phi dash xi n. So epsilon n plus 1 and epsilon n are of opposite sign. Okay, so let us explain that thing. Okay, let me explain. Okay, let me explain. So I'm talking about minus phi less than phi, you have a g dashed, right? G dashed alpha less than 0. So it follows from the error equation. What is your error equation? Epsilon n plus 1 equal to epsilon n g dashed xi n, right? Z dash xi n. Okay. So you see epsilon n plus 1 and epsilon are of opposite sign, right? So opposite signs because less than epsilon n, okay, they are opposite sign, and epsilon n tends to 0 as n tends to infinity, okay, they are opposite sign, so that xn oscillates between about alpha with diminishing amplitude and tends to alpha. Xn oscillates about alpha, you see xn oscillates about alpha, so you have a spiral solution oscillating between alpha. This is your alpha, and xn sometimes on the right hand side, sometimes on the left hand side. This is called oscillating about alpha with diminishing magnitudes, okay, amplitude and tends to alpha. This is called spiral solution. And what about the second case? This is number 2. Second case is 0 less than gx g dash x less than 1 in this case, okay. So you have in the second case number 2, 0 more than g dashed alpha. In this case you have g dash in the diagram less than 1. So phi dash xi n greater than 0, right? Phi dash xi n is positive, and epsilon n plus 1 and epsilon have the same sign, right? They have the same sign, okay. That is why xn tends monotonically to the root alpha from one side, one side only. You see xn tends to alpha monotonically from one side only, just from one side. If you, this is your x naught, then it will approach from this side. If x naught is this one, this will approach from this. So this is the cases for the convergence, okay, clear. And these are the, look at that below, number 3, this is divergent if mod g dash x greater than 1, and this is also the cases for divergence. This is staircase divergence, and this is spiral divergence. So these are the 4 explanation, beautiful and most important explanation of the Newton fixed point iteration method, okay. And estimation of error can be already calculated. You can calculate, define hn equal to xn plus 1 minus xn, and xn plus 1 you can write alpha minus xn, alpha minus xn. So you have a error calculation. Error can be calculated like this, or already we have calculated epsilon n plus 1 equal less than equal to k mod epsilon n, and similar manipulations. After that you have an error equation. This is the error equation, estimation of error. You can estimate the error, okay, by this method. So this gives you, this will give you the estimation of error of the fixed point iteration method, that is modulus of epsilon n plus 1 less than equal to k by 1 minus k modulus of hn. So this also gives you the estimation of error also. So a lot of things we have analyzed in fixed point iteration method. Also we have a graphical method, so I am not talking about the graphical method in this my lectures. That is not so important. So mainly you have 5 methods in your syllabus, that is Newton-Raphson method, bisection method, secant method, tabulation method, and regular falsy method, and the fixed point iteration method. So you have 6 methods. So in the mostly the first convergence method is the Newton-Raphson method, because it's quadratic convergence, rate of convergence is quadratic. So that is how in my all the lectures of roots calculation you have learned about how to calculate the errors, estimation of error, error equation, rate of convergence of the method, and the method itself, and every method has a geometrical interpretation. So follow my lecture videos on YouTube channel, and subscribe and share with your friends also. Thank you all of you.